So welcome everybody to the second of today's seminars. It's a huge pleasure to have Philip Easo speaking to us from California, and he's going to talk about percolation on finite transitive graphs. Over to you.
Okay, thank you, and thanks to the organizers for the invitation. So I'm going to be talking about a project that's been going on for about 2 years with my supervisor, Tom Hutchcroft, which is to understand what can be said about like the most basic questions about percolation on finite transitive graphs, which is, it's a context where people don't normally study percolation. So what I'm going to start by doing is defining the terms percolation and transitive, and also give some background on, the big questions in percolation on infinite transitive graphs that sort of motivated this. So first, percolation is, for us, it's always going to be, you have a graph G, which is countable, locally finite, and connected, and I'm not going to write those. You have some parameter P between 0 and 1, and then bond percolation is just the law of the random spanning subgraph of G, where you just independently include every edge with probability P. So it's like the simplest way that you can form a subgraph like that. And the connected components of the spanning subgraph are called clusters. That's the convention. Okay, so one of the settings where people study percolation a lot is when G is an infinite transitive graph. So really this was a project that started with Benjamini and Schramm in '96. Before that, people studied percolation mainly on Euclidean lattices in this context. But they said, what about if we considered an arbitrary infinite transitive graph? So transitive just means that given any two vertices in your graph, you can find an automorphism, like a graph symmetry, mapping one vertex to the other. So the automorphism group acts transitively on the set of vertices. So here I've got some examples. You can have the Euclidean lattice ZD, of course. You could also take a regular tree. And in general, you could take any Cayley graph of an infinite finitely generated group. And those are really like the most interesting ones. Okay. So here's what you get for free if you start trying to work on percolation on this setting. You get that there's some critical parameter PC that might be 0 or 1, or anywhere in between, such that if you do percolation at that parameter, then the probability that there is an infinite cluster, an infinite connected component, is 0 if you're below PC, 1 if you're above PC. And you don't get to know what it is at PC. You can know that it's either 0 or 1, but not the number. So this comes for free just by like Kolmogorov 0-1 law and monotonicity of things. This is for free. So then, the major questions, we'll see one more later, but here are some of the major questions at this level of generality. And these are ones that Benjamini and Schramm introduced in their work. When is the critical parameter strictly between 0 and 1? So this is called the phase transition being non-trivial. It's always, well, I'll say what's known about these in a second. When you have an infinite cluster with probability 1, how many infinite clusters are there? Like, is it unique? How does it depend on the graph? And then finally, this question mark one, what is the probability at PC? And this is maybe, the biggest question. This is equivalent to what's called continuity of the phase transition. Okay, so let me just sketch what is known about these, because this is kind of what motivates the questions we're going to be asking on finite graphs, finite transitive graphs. So the first question, when is PC strictly between 0 and 1? Well, you basically get for free by a branching argument that PC is not 0 ever. So the question is, when is PC strictly less than 1? And if you think about just taking, Z or anything one-dimensional like that, it's pretty easy to check that PC has to be 1. Like if your parameter P is strictly less than 1, then you're not going to have an infinite cluster. So you can rule out one-dimensional examples like that. But Jimmy Coupin, Goswami, Ralphie, Severa, and Yadin in 2018 proved the converse, which was open for a while, which was that if you're not one-dimensional, then PC is strictly less than 1. Okay, the next question is how many infinite clusters are there? And it was, well, it turns out to depend, or conjecturally depend, on this property called amenability. So our graph G is called amenable if the boundary to volume ratio of finite subsets in your graph can be made arbitrarily small. So it doesn't matter whether you count this as a vertex or edge boundary or whatever, you'll get the same answer. So for example, the Euclidean lattice is amenable, but the regular tree, a free regular tree, is not. And Eisenman, Keston, and Newman in 87, and Burton and Keene with Slicker proof in 89, proved that if G is amenable, then whenever you have an infinite cluster, it's unique, essentially. The converse remains open, and that's another one of the major questions at this level of generality. You can prove, for example, for a regular tree that you do have multiple infinite clusters. In fact, it has to be infinitely many. But for an arbitrary non-amenable graph, it's not known. Okay, and then this last one I mentioned, what happens at the critical parameter is the phase transition continuous. Again, it's conjecture to hold whenever G is not one-dimensional, and we'll see this one-dimensional thing come up later. They're kind of the bad guys in the story. But it's open even for the three-dimensional Euclidean lattice. And this is like a major problem in the area. Okay. So the idea for, one of the motivations for our work was this general study of percolation on infinite transitive graphs. And we wanted to somehow bridge this with high degree graphs. I mean, that's one of the objectives. One of them was just to generalize to bounded degree finite transitive graphs. Another was to form a bridge all the way to the complete graphs. So, the other context where people studied percolation is in the Erdős-Rényi model, where the base graph G is just the complete graph on n vertices. And so what I'm going to do just now is motivate our definitions, or define our definitions for the complete graph. This is totally not how people talk about percolation on the complete graph, and people ask many other questions on the complete graph. But these are like the properties that are going to be relevant for us on percolation on finite transitive graphs. And I just want to motivate it here because I think most people are familiar with the basic properties of the Erdős-Rényi model. So we're going to, in a given percolation configuration, we're going to enumerate the clusters, the connected components, K1, K2, and so on, in decreasing order of the number of vertices they contain. So this absolute value of K1 means the number of vertices in it. And then this norm of K is not a norm, but it's the proportion of vertices contained in the cluster K. So the proportion of vertices in the total graph that belong to this particular cluster. Okay. So if you take, percolation on the complete graph, then, it's known since Erdős-Rényi that you have a percolation threshold at 1/n. So what that means is that if you take a sequence of parameters that's supercritical with respect to that, so for example, you could formalize it by saying the limit of Pn/n is greater than 1, then you have a giant cluster with high probability. For some epsilon, you have the largest cluster contains proportion at least epsilon of the total vertices with probability tending to 1. And conversely, if your sequence is subcritical, and the definition is analogous, then the largest cluster is not linear sized with high probability. So for any epsilon, the probability of the largest cluster contains more than proportion epsilon vertices goes to 0. Okay. Another one of these basic properties is that it has what we all call the supercritical uniqueness property, that for any supercritical sequence Pn, the second largest cluster's density goes to 0 in probability under percolation of that parameter. So this is like saying that, the previous statement tells you that when you're supercritical, you have a giant cluster with high probability. And the second one is telling you that it's unique because the second largest cluster is not linear sized. And then the third property is the supercritical concentration property. And so this one is slightly more subtle, but it's saying that if you take your supercritical sequence, this unique largest linear sized cluster, its density is concentrated around its mean. It's the same as its variance going to 0, or however you want to mention it. And this is like slightly more subtle, but it's really the starting point for any further study. For in our context, it'll be the starting point for further study, because now you somehow know that you have a well-defined density for the giant cluster, and it's measured by its mean. That's sort of the way to think about it. Okay. So this brings us to like our context, which is studying percolation on arbitrary finite transitive graphs. So let GM be an arbitrary, sequence of finite transitive graphs with its number of vertices tending to infinity. So here are some examples of things that we could that count. You could take the complete graphs. You could take the hypercube. You could take this discrete torus, the two-dimensional discrete torus. You could take two copies of two complete graphs and then pick a matching between the vertices. This is also vertex transitive, or what we're just going to call it transitive, but it's not edge transitive because, but it's vertex transitive. So it counts for us. And in general, any Cayley graph of a finite group is fine. Okay. So now in this level of generality, we can ask, when does it have, and these are maybe like the coarsest questions we could ask, when does it have a percolation threshold in the sense of the complete graph? When is there a sequence of parameters that plays the role of percolation threshold? Given that, you could define, what it means to be supercritical with respect to it. And then you could ask, does it have the supercritical uniqueness property or the supercritical concentration property? And so the goal for at least the first half of this talk is to outline our answers to these three questions. It turns out, rather surprisingly, that supercritical uniqueness comes first. So what I mean by that is we proved it first, and also our proof really works that way. So we need to prove supercritical uniqueness before the existence of a percolation threshold. This is a little strange because how do you define what it means to be supercritical unless you have a percolation threshold with respect to which to be supercritical? So what we need is a more general definition of the supercritical sequence that also makes sense when you don't have a threshold sequence. So here's that definition. You say that a sequence of parameters is supercritical if for some epsilon, for every n, the probability that the largest cluster has density at least epsilon is at least epsilon, not just at your parameter, but a little below your parameter. So it's saying that you have a giant cluster with good probability, even at a slightly lower parameter. And you can see that this coincides with the usual definition of supercritical if you happen to have a sequence. Cool. Okay. So really, we need to divide into two cases when you have when the sequence of graphs has bounded vertex degrees, uniformly bounded over the whole sequence, like the sequence of d-dimensional tori, and then the general case. In the bounded degree case, all the answers will be much simpler to state. But in the general case, there will be some counterexamples we'll have to deal with. So our work started by trying to solve this conjecture of Benjamini from 2001. It is the same Benjamini as the Benjamini and Schramm from earlier. He asked, does Gn, so under this additional hypothesis that it has bounded vertex degrees, does it always have the supercritical uniqueness property? And so this was known for tori using methods highly specific to that, and also for not necessarily transitive expanders. But the conjecture is for an arbitrary sequence of finite transitive graphs with bounded vertex degrees. And so that was a starting point for our work. And what we showed is that in this bounded degree setting, the answer to every question is yes. So you have the supercritical uniqueness property, you have a percolation threshold, and you have the supercritical concentration property. Hopefully, if we have enough time, I'm going to try and sketch a proof of this conjecture, like the first step, which was the proof of the supercritical uniqueness property in the bounded degree case. Let me also mention like a question that isn't really, the question we're trying to address, but is also an interesting question, and also just to like clarify, this is not what we mean by the existence of a percolation threshold. This is the analog of the is PC less than 1 question that I mentioned for infinite graphs. This is the finite version. And this was addressed by Hutchcroft and Twinton. So what they showed is that if your sequence of graphs has at least 1 plus epsilon dimensional growth in some sense, so in some sense, you're not like the sequence of cycles or even a slightly thickened sequence of cycles, but you're a little more than that, then PC is less than 1 in the sense that you have a non-trivial phase where you have a giant cluster. You could also phrase that as saying there are supercritical sequences, right? Okay, and then there's one other corollary from our work on concentration that I want to mention, and that's, well, that's the following. But to state it, I need to define what it means for a sequence of graphs that converge locally. So if you have a sequence of transitive graphs converging to a graph G, then we say that it converges locally if for every radius, the ball of that radius in your sequence of graphs is eventually isomorphic to the ball in the target graph. So in this example, I'm trying to show how if you have a sequence of d-dimensional tori, then that will converge locally to the d-dimensional lattice, because for any fixed ball, eventually the torus, you will only see, I mean, it'll look the same as the lattice in the limit. So, right, I said that our work is trying to somehow bridge the infinite transitive graph story and the high degree story in one story. But to really link up with the infinite transitive graph story, like somehow we need that the percolation, like the giant cluster density or something on the sequence of infinite transitive graphs, I mean finite transitive graphs, has to be related to the infinite transitive graph limit, right? That's what it would mean for our stories to link up somehow. Otherwise, we're not really bridging. And okay, so here's what we showed. We showed that if you have some fixed parameter P that is supercritical for the whole sequence of graphs, i.e. the sequence P is supercritical for your sequence of graphs, and they converge locally, then the giant cluster density converges to the infinite cluster density in this sense. And this is somehow like related to a well-known conjecture of Schramm called Schramm's locality conjecture. That's phrased for infinite transitive graphs. And what that says is if you have a sequence of infinite transitive graphs that converges locally, and you have this additional hypothesis that the lim sup of the PCs is bounded away from 1, it turns out to be equivalent to just requiring every PC to be less than 1 because of more recent work. But if the sequence of graphs converges locally, then so does the percolation thresholds. So somehow the percolation threshold is determined by the local geometry of the graph. We haven't solved this, and although we're trying very hard, and our result is slightly, it's neither stronger nor weaker, it's a different thing. Also, let me just mention that our theorem here, the analogous, we can show the analogous thing for infinite graphs. If you have a sequence of infinite graphs and you have a parameter that's uniformly supercritical along the sequence, then the infinite cluster densities will converge. Also, this conjecture of Schramm, something like it for finite graphs, we expect to hold, not sure exactly under what condition, and maybe something like not being too one-dimensional, but basically thin cycles definitely mess things up. Okay. So this brings me to like a very well, maybe initially surprising thing, which is this. So suppose you have a sequence of graphs that are nice in whatever that means, and they converge locally to a graph that's non-immutable. Well, by that conjecture about non-immutable graphs and the infinite cluster, there should be some supercritical parameter P where you have multiple infinite clusters, actually infinity many. But then our result tells you that the supercritical giant cluster along the sequence is always unique. And its density should converge to the infinite cluster density in the limit. So how are the uniqueness of the giant cluster along the sequence and the non-uniqueness of the infinite cluster in the limit consistent with each other? It kind of seems like initially, or at least it seems to me initially, that this would be in tension because the densities converge to each other. So But here's sort of what happens, or what we expect to happen. And this is verified, for example, if the sequence of graphs happens to be an expander sequence converging to a non-amenable graph, this is known. So what happens is on the left, I've got, my finite graph that is converging to the regular tree on the right. And on the left, I've got some ball of large radius where my finite graph looks the same as the limit graph. And what happens is if you start exploring the percolation cluster, if you start revealing edges and exploring what the percolation clusters look like, it looks like you have multiple giant clusters growing. But because you're on a finite transitive graph, they will always wrap around and connect to each other. So for example, if you just cut out a piece of a 3 regular tree, this wouldn't be vertex transitive, because the leaves would not be the same as the vertices inside. So that doesn't work. And any way you try to continue this to make it transitive, you're going to force these apparently multiple giant clusters to connect to each other. And in the limit, these will actually disconnect. So somehow the metric distortion of the graph distance versus the distance along the giant cluster will blow up. Great. Okay. And let me just mention what happens in the general case, roughly. This is not really the focus of the talk. But when you go to the general case, so this is arbitrary sequences of finite transitive graphs, but possibly unbounded vertex degrees. So complete graphs, for example. It's no longer true that every answer is yes. So for example, you have this really simple counterexample I sketch with 2 complete graphs and a matching between the vertices. It doesn't have the supercritical uniqueness property. For example, the sequence of parameters 2 over n is, here's what happens when you percolate that parameter. In each of the complete graphs, you're just doing Erdős-Rényi. And 2 over n is supercritical. So you have supercritical Erdős-Rényi. So you have a giant cluster in each. But the number of vertices in between, there are number of edges in between, there are n edges, each present with probability 2 over n. So this converges to a Poisson process. So there's a positive probability that none of the edges will be present. Yet with high probability, you have a giant cluster in each. And so you have two giant clusters with good probability. And it's very easy to generalize this construction to come up with a class of them that we call molecules. And so molecules are really sequences of graphs where you can partition the vertices into finitely many pieces. In each piece, it's just a dense graph, and the number of edges in between is linear sized. Additionally, this linear set of disconnecting edges is automorphism invariant. So it's a little more structured than what might be. And basically, our theorem is that these are the only obstacles to all 3 of these problems, all 3 of these questions, which sort of highlights. So it's kind of obvious that these fail supercritical uniqueness and so on. It's the converse that's difficult, and this kind of highlights the difficulty in the general case. Your argument needs to carve out this really specific, highly structured counterexample. All you get to assume is non-uniqueness or something, and you need to somehow find this automorphism invariant set of edges and so on. Okay, so are there any questions at this point before I start giving a sketch of the proof of Benjamini's conjecture? Because I feel like this next half will be slightly more technical because it's the proof itself. But if anyone has questions about the general background. No? Okay. Great. So yeah, in the remaining time, I'm going to try and sketch our solution to Benjamini's conjecture, which was what started this whole thing. And this is the statement that if you have a sequence of finite transitive graphs with uniformly bounded vertex degrees and volume diverging, then you have the supercritical uniqueness property. So a key tool that we're going to need, and this is really typical in percolation. Sharp thresholds are a really key tool in percolation in general. So here's the sharp threshold result that we're really going to rely on. And it's just a corollary of Talleyrand's sharp threshold result from '94. And it's going to tell us that since our base graph is automorphism invariant, if you have an increasing event, so by increasing, I mean it's an event where if you add more edges, it still holds. Like if it held and then you add more edges, it still holds. So for example, the event that two particular vertices are connected, or the event that the largest cluster has exceeds a certain size. If you have one of those events, and it's invariant under automorphisms of the graph, then it has a threshold width that's 1 over log of the number of vertices. So what I mean by that is, if you had a good, you can find some region in your between 0 and 1 of width. You know, if you take, how should I phrase it? If you have a good probability at some parameter of this event occurring, and then you go up more than this amount, then it will happen with high probability. That's one way you could phrase this, but it's just the typical, you know, sharp threshold notion. Okay, so this is the key sharp threshold result we're going to need. So let's start building our proof. Let's fix a supercritical sequence of parameters Pn, which we're not claiming things about its existence. I mean, the existence of such a sequence comes from the work of Hutchcroft and I, which really is a different flavor. I mean, this requires like structure theory of you know, finite transitive graphs and so on. But okay, so you have this sequence of supercritical sequence of parameters. By definition, we can find some constant delta such that Pn minus delta is still supercritical. Okay, this is from the definition. And our goal is to show that the second largest cluster's density tends to 0 in probability under percolation of parameter Pn. So the first step in our argument is to find a smaller parameter Qn, like lower than Pn, where we do have control of everything, including the second largest cluster. And then from that, deduce what we want back at Pn. This is how the argument goes. So this claim is where we find that good sequence Qn. So I claim that there's a sequence Qn that's always between Pn minus delta and Pn. So being at least Pn minus delta guarantees that Qn will be supercritical. That's the point of that one. And also it has the supercritical concentration property at that parameter. Like the density of the largest cluster at that parameter is concentrated around its mean. So here's the proof for why such a sequence exists. Fix your n, and I have to give you a parameter Qn. Define a function m from 0, 1, where m of p is the median density of the largest cluster under percolation of parameter p. So the fact that it's median is not important, just you have a good probability of being above and below this number. Then here's, I kind of sketched what this function might look like. It's this pink thing. So it's some non-decreasing function. Of course, in reality, you've got a finite graph. So this is going to have some discontinuities. It's going to be some piecewise constant thing, but that doesn't affect the proof at all. So let's just pretend it's continuous. So, and also on this graph, ignore the yellow lines for now. I've labeled our PC minus delta and our PC, and we're trying to find some parameter Q in this region that has the property. So here is like a totally elementary fact, and it's just pigeonhole principle, that if I give you any n, you can find some parameter Q in this region such that if you look at Q plus delta over n and Q minus delta over n, the median doesn't increase more than 2 over n. This is really, so I mean, all you do is you divide your interval into n or 2n pieces, and you just pick the interval where things increase the least, and then you pick your midpoint of that. It's just the pigeonhole principle.
Can I just check that PC here is PN?
Yes, my bad. Yeah, totally. Thank you.
Thanks.
Yeah. Thanks. So, right, I mean, just by pigeonhole principle, you can find this, you can always find this parameter where this increase is at most order 1 over n. Just because the median is non-decreasing, it takes values between 0 and 1. That's okay. Now, note that, and then again, this is just immediately by the definition of the median. If you're at Q minus delta over N, then with probability at least a half, the largest cluster has density at least the median at Q minus 2 over N. So this is just, by rearranging these things and the definition of median. And then the analogous statement here. Okay. So I've just rewritten these two conditions at the top here. And now we're going to apply our sharp threshold result from Talleyrand. So we choose our capital N to be root log of the number of vertices. So something much more than log. It's much less than log. Because that way we know that for any automorphism invariant event, increasing event, like for example, this event or this event, these are automorphism invariant increasing, or rather the first one's increasing, the next one's decreasing. They're automorphism invariant, so their threshold width is at most order 1 over log the number of vertices. And that's much less than delta over N, which is because of our choice of N. So what that implies is since we have probability at least 1/2 of this event down at Q minus delta over N, it must actually happen with high probability all the way up at Q, because we've gone up delta over N, which is more than the threshold width. And then the analogous result here. But notice that we're done. I mean, now what we've got is that the density of the largest cluster K1 under percolation of parameter Q is sandwiched around M of Q, with the window shrinking like 1 over N. And this is happening with high probability. So it's concentrated around that value, and in particular around its mean. Cool. Okay, so at this point, we've got our sequence of parameters Qn that is still supercritical, but smaller than Pn, where we have concentration of the largest cluster. Okay, here's another claim that I'm not going to prove, but it's not trivial, but it's also not the hardest step in the proof. And that's at this sequence of parameters Qn, you also have uniqueness of the giant cluster. So the second largest cluster has density tending to 0 in probability. And basically, this is just because concentration implies uniqueness, and concentration is a stronger property than uniqueness. To see this, the idea is basically if you could have 2 large clusters, i.e. if you have non-uniqueness, then the largest cluster with good probability could be this one, or it could with good probability be, the 2 of them with connected to each other, which is much larger than the initial largest cluster. And then you use positive association and so on to make this work. Okay. So now we have to go from these good properties at Qn to our desired properties at Pn. And for this, we need to translate between the two percolations. And for that, we have this object called a sandcastle. So let's set up our contradiction. Assume for contradiction that we don't have supercritical uniqueness at Pn. So there exists some epsilon such that for every n, there's a good probability that the second largest cluster has size at least epsilon. Also, we know that under Qn, the largest cluster's density is concentrated. So by passing to a subsequence, let's make it concentrate to this constant alpha between 0 and 1. So here's like the most technical definition. A subgraph of a base graph G is called a sandcastle if it has these 2 properties. The first one is just that it contains a good proportion of the vertices. So density of S at least epsilon. So it's large. The second is that if you start with this graph, this subgraph, and you do percolation of parameter Qn over Pn, then with good probability, the largest cluster left over will be small. So that's kind of what I've tried to illustrate here. This graph here might be, this subgraph might be a sandcastle. And if it is, that would mean that with good probability, if I do percolation of this parameter, you end up with only small pieces, none of them exceeding alpha over 2 times the number of vertices in the base graph. So does that definition make sense, at least? Even if it's not clear why it's useful. Okay. So the reason it's useful is because, like I said, we want to relate percolation of parameter Pn and percolation of parameter Qn. But there's a really natural way to get a percolation configuration of parameter Qn from one of parameter Pn. And that's just that you do percolation on the percolation subgraph with parameter Qn over Pn. Right, so like, if you want to sample from Qn, you can sample from Pn and then resample the open ones, Qn over Pn. So that means that if we see all of these edges in the sandcastle are open at Pn, then with good probability in Qn, they will fall apart to just be small pieces. That's what this means. Okay. So my claim is that eventually, with good probability under Pn, K1 or K2, either of the two largest clusters, is a sandcastle with good probability. So I'm going to try and do this proof by a drawing, and we'll see if this is understandable. But so suppose that this is not true at some parameter n. So the probability that one of them is a sandcastle is at most epsilon over 2. We know that with probability at least epsilon, both the largest and the second largest clusters are large. Density at least epsilon. That was our contradictory hypothesis. So just by a union bound, we know that this event holds with probability at least epsilon minus epsilon over 2. So with good probability, here's what we have. Under Pn, both of the largest clusters are large, and neither of them are sandcastles. Okay. Then here's a bad situation that could happen with good probability. That's why we have a contradiction. So suppose we want to sample our configuration of parameter Qn. I said we can first sample our configuration of parameter Pn and then resample by Qn over Pn. So what might happen with good probability is in our first step, we could find these two largest clusters, K1 and K2, that are both large and neither sandcastles. That could happen with probability at least epsilon over 2. That's what we've got. But then when we go down to Qn, because K1 is large and not a sandcastle, that means that with probability at least 1/2, it doesn't fall apart into small pieces. So with probability at least 1/2, it leaves some large piece after passing down. Similarly with K2, it has probability at least 1/2 when you go down of leaving a large piece, where each of these large pieces means at least density alpha over 2, but that's not really important. Also, every edge that was initially on the boundary, all these closed edges that were on the boundary of the clusters above, are still closed in the clusters below. So these two large pieces left over aren't connected to each other. So what we've constructed with good probability is a configuration for parameter Qn where you have two large clusters. But that's a contradiction because we said that we have uniqueness of the giant cluster under Qn. Right. So now we know that K1 or K2 is a sandcastle. My next claim is that there is a deterministic sequence of subgraphs Sn. So every Sn is a subgraph of Gn, and they're all large. And they have the following property. If I do percolation of parameter Qn, but I only use edges outside of Sn, in fact, not just outside of Sn, but outside of Sn, so maybe this is Sn, outside of Sn and the edge boundary, I still have concentration of the largest cluster at density alpha. So what we have already to start with is that at parameter Qn, the largest cluster has density concentrated to alpha. Now what I'm asking for is a sequence of subgraphs I can delete such that it's still concentrated at density alpha outside of this sequence of large subgraphs. Okay, so my proof is really like a probabilistic method proof. I'm going to say construct one randomly. And what I'm going to do is say, we know with good probability, if I pick a particular vertex, its cluster is a sandcastle under parameter Pn. That's what the previous result tells you. I mean, it tells you one of the two largest clusters is a sandcastle, and by transitivity, it tells you a particular vertex's cluster might be a sandcastle. And my claim is that if you pick it randomly, then with probability, like with high probability, that cluster will do. So given that the cluster at a vertex is a sandcastle, with probability tending to 1, that will work as a subgraph Sn. So to prove this, and then you can pick any, right? It doesn't matter which one. So to prove this, suppose for contradiction this wasn't the case. So that would mean that with good probability, I might explore the cluster under Pn of a particular vertex. So that's what's happening here. And here. And with good probability, I can do that, but then the omega Qn configuration outside of this set will, with good probability, not have a largest cluster of density around alpha. Right, that's the defining thing. So here, what I've drawn is, in our coupling of Pn and Qn percolation, I might first explore the cluster in Pn, then explore the edges in Qn outside, and discover that the largest cluster outside has density away from alpha with good probability. But then to finish sampling my Qn configuration, I could then resample the edges on the interior of this original cluster. And because it's a sandcastle, it will fall apart into small things with good probability. So what we've constructed with good probability is a Qn configuration where none of the clusters have size around alpha. Right? And these closed edges along the boundary are going to stop anything inside connecting outside. So what we've done is we've contradicted concentration of the largest cluster under parameter Qn. Okay, so now we have our deterministic sequence of subgraphs Sn that we've constructed. Here is the final claim for this proof. What I claim is that is going to contradict concentration of parameter Qn, concentration of percolation of parameter Qn. So that's what this claim says. This claim says that eventually the probability that the largest cluster under Qn is abnormally large, right? It's supposed to be alpha, but here it's alpha plus a constant, happens with good probability. And once we show that we're done, we've broken concentration at Qn. And the proof, okay, here's the proof. You fix your subgraph Sn, which is a deterministic subgraph. And that's what I've drawn here in white. And what you do is you say, look at the set of vertices in Sn that have the property that their largest cluster is reasonably large, size alpha over 2. So I've drawn these as the pink vertices, and they are all in a large green blob of size at least alpha over 2. That's their defining thing. And okay, we can ask ourselves, how many such vertices are there? Like, what's the expected number of vertices? And then we're going to get into the probability that they exceed some size. So we know that the largest cluster in Qn is concentrated around alpha. So a particular vertex has probability approximately alpha of being in a cluster of size approximately alpha by transitivity. So the expected number of this is under Qn is approximately alpha. So the probability that it exceeds alpha over 2 is approximately at least alpha over 2 by Markov. And so I put some 3s here to make it actually true eventually. So what we've got is with good probability, you have many of these vertices doing this, but we have non-uniqueness of the giant cluster in Qn. And we know by definition of Sn, by construction of Sn, outside of this, we have a largest cluster that's of density around alpha with high probability. So we have this cluster outside that's large. We have many vertices in here that are large, in large clusters. And we have uniqueness of large clusters. So all of these must actually be connected to the largest cluster. That's what these green lines are. So the total density is actually around alpha plus however many pink vertices there are, which is like alpha over 3 times the number of vertices in Sn, which is like epsilon. So with good probability, the largest cluster in Qn is abnormally large. That's our contradiction. Great. So that's the end of the proof of Benjamini's conjecture, like the uniqueness, supercritical uniqueness. Let me also mention, for people who are familiar with percolation on infinite graphs, so that result of Burton and Keene about uniqueness of the infinite cluster on amenable infinite transitive graphs. You know, finite, if you take the naive definition of amenable, every finite transitive graph is amenable. So you might think that maybe the Burton-Keene proof works for finite graphs. But it really doesn't, because, and this is one of the key differences between, or key challenges about working on finite graphs, is that we care about giant components that have a positive proportion of the vertices. Whereas on infinite graphs, often things are about an unboundedly large size, because that's the same thing as being infinite in that context. So Burton and Keene really tells you that it's, you know, you're unlikely to have a vertex with like a trifurcation, 3 long paths leaving it that are not disconnected in some region. But this isn't really a priori in tension with having multiple giant clusters. This is about long clusters or unboundedly large clusters, not giant clusters. Yeah. Great. So let me finish with an open problem that we weren't able to solve. And this seems like the difficulty seems related to the difficulty in general in percolation of ruling out one-dimensional examples. So let Gn be a sequence of finite transitive graphs with size going to infinity and bounded degree. So as in Benjamini's conjecture. Then we say that Gn has the general uniqueness property if for any sequence of parameters, the second largest cluster has density going to 0 under percolation of parameter Pn. Now, notice that this is subtly different to the previous, like the supercritical uniqueness property. That was the same statement, but just for supercritical sequences. Now, for typical examples, it should be that as you go to the percolation threshold, the density goes to 0. I mean, that's what happens in the complete graphs. So really, like in that case, you know, if you have the sequence that the phase transition is continuous in that sense, these properties are the same, right? Because if you're supercritical, our argument does it. If you're around the phase transition, you just have no giant cluster at all, so it's trivially true. And if you're subcritical, there is no giant, so it's fine. But in discontinuous phase transitions, you really can have multiple giant clusters at the phase transition. So here's some examples. I mean, the trivial example is a sequence of cycles. And if you do your percolation at parameter around 1, then you've got like 1 minus 1 over n. Then what you've got is this Poisson process of dead edges. And maybe I should have colored the edges instead of the vertices, but dead edges around the boundary of the cycle. And since it's a Poisson process, you could have like a good number, you could have like 2 of them with good probability. And then you would have 2 giant clusters. So you have non-uniqueness there. But there you also have a discontinuous phase transition. In fact, you can slightly stretch this example to have this really elongated torus. So n by 2 to the n torus. And the same kind of example works. Basically, it's not straightforward to prove. You have to use like Russo's, like the 2-dimensional percolation results. But you basically get a Poisson process of these cut sets that can disconnect giant clusters. So the same thing happens. And again, you have a discontinuous phase transition. So it might just be that multiple giant clusters at criticality are really a feature of a discontinuous phase transition, and eliminating that is similar to eliminating discontinuous phase transitions. If that's the case, then this is a really hard problem. So, but we'll see. So the conjecture, which is of Noga, Alon, Benjamini, and Stacy from 2004, is that if you just rule out this counterexample, this isn't how they phrased it, and we don't know if this is really the bound, like why they have this specific bound, but this bound does eliminate the specific class of counterexamples. If the diameter is just below the volume in this sense, it's little o of the volume over log of the volume, then Gn has the general uniqueness property. So you have a unique giant cluster even at the even around the percolation threshold. And this would be interesting even if instead of this you made it, 1 plus epsilon dimensional growth. You can think of being one-dimensional as like saying your diameter is similar to your volume. Here they're saying your diameter has to be a little smaller than your volume. If you made it really like 1 plus epsilon dimensional smaller, this is still open and would be super interesting. So this is open and we don't know how to prove it, but if anyone's interested in having a go, then that's that. Thanks for listening. I think it's the end of my presentation.
Thank you very much, Philip. That was a beautiful talk. Can I invite any questions? So I was wondering if I could ask you to say a little bit more about these molecules. It seems kind of magical to me that these are really the impediment. I mean, as you say, one way it's kind of obvious, but how you show that that's essentially the only set of things that can.
Right. Yeah. So the way that the proof goes to identify these as the only counterexamples is kind of technical, but so basically the overall strategy is the same as the bounded degree strategy. But the sharp threshold result is what breaks down. Basically, when you're working with high degree things, your PC might be close to 0. And so the usual Talleyrand sharp threshold breaks down. But there's this sharp threshold result of Bourgain, and recently it was sharpened by Hitami. Basically, it tells you that, well, let me say this. Our proof still works if you have a sharp threshold for the event that the largest cluster exceeds a particular constant. If that's always true in some uniform sense, our proof still works. So it's about getting that. And this is the class of examples that fails that. And the way you can prove that is you say, okay, I want to try and use Bourgain/Hitami to prove these have sharp thresholds. Suppose they don't, they have coarse thresholds. Then Bourgain/Hitami tell you that there's a bounded number of edges that play a decisive role with good probability. There's a bounded number of edges such that if you have them all on compared to what they actually are, there's a good chance you'll change whether the event holds. Mm-hmm. Then with like a very careful repeated sprinkling argument where we increase the parameter like arbitrarily many times and some resummation like the transitivity arguments, you can basically cut this down into a single edge that has a decisive role to play. Once you're at this single edge, then you basically by Rousseau's formula, like just general like the derivative of an increasing event thing, you can see that this has the property required here. So it's automorphism invariant basically by construct. Well, it's also if you take its orbit, it will have the role of these disconnecting edges, and the rest is
I see. Thank you very much. It was a very nice sketch. I'm sure the details are much more complicated, but that gave a nice idea. Does anybody else have any other questions?
What happens if you move away from transitive? I mean that's sort of just too vague, but there should things like, if you had a random deregular graph and did percolation on it, sort of everything has to work. But the question is there a sort of reasonable, might there be a broader class where things go through?
I don't have a sense about that at all, really. I think, I mean, like every argument we really rely on is crucially based on transitivity. Even these like sharp threshold results that are kind of the heart of everything are based on events being automorphism invariant and so on. So I don't have a sense at all about a broader class than that. I mean, you can certainly take quasi-transitive graphs where you have like a bounded number of vertex. And in general, you could push that a little more perhaps. Maybe you can take multi-graphs with similar properties, but as soon as you abandon any symmetry assumption like that, it's not in the realm of these techniques.
Were you waving?
Hiya, Philip. Thank you very much for an interesting talk.
Oscar, can I take Emmanuel's question first?
Oh, sorry, I didn't see. Sorry.
Oh, okay, thanks. Sorry about that. I was wondering, you mentioned this conjecture of Schramm at the beginning.
Yes.
And about local, what sequence of graphs converges locally. So does this work also if you consider the notion of Benjamini-Schramm convergence?
Yeah,
where
it's it's the same thing because they're transitive, right? Or
in your case, they're transitive. Yeah. Okay. Sure. Yeah. No. Sure. Yeah. I understand. And so this was my first question. My second is actually so yes. So you say you use the fact that it's transitive, but if you take a Schreier graph and under some conditions, maybe could you say
it's possible. I don't want to claim anything that I'm not sure, but
and everything you say seems to be completely oblivious to the particular structure of the group. That you look at. So
you mean this finite graph stuff or the general? Okay.
No, yes. in your main theorem. So there is no. I mean, it just holds for an arbitrary sequence of finite transitive graphs. Do you have properties that you could identify that will be able to tell what sort of?
Oh, so you're muted, I think, or at least I can't hear you anymore. Sorry
about that. No, I'm saying.
Yeah. Right.
Yeah. So yeah, your properties hold for arbitrary sequences of transitive graphs. If you take some particular sequences, can you say some more? Or
right?
I mean, can you distinguish expander graphs, non-expander graphs, or
right? Yeah. So yeah, thank you. So we in this story of finite transitive graphs, there isn't too much. What we can do is I can exactly tell you if you have mean field density for the supercritical giant cluster. And essentially, because you see these molecules, you can kind of make macromolecules where it's the same thing, but the number of atoms diverges. And this is somehow the only obstacle to mean field behavior. So I can tell you when it's mean field or non-mean field, the supercritical density. But beyond that, certainly like being an expander sequence gives you a lot more tools to prove things. So in this paper of Alon, Benjamini, and Stacy, they proved many things using expansion. Instead of transitivity, but some other papers use both. So you can use things like that. But no, we don't have anything that really distinguishes between the two. I think in general, high degree things are sort of mean field territory, like they should be in general. So of course, in the infinite graph setting is different. And there.
So for infinite graphs, you said at the very beginning that there is this distinction. You can I mean, conjecturally at least, you can tell immutable graphs.
Yes.
By the fact that PC, there are two critical parameters. But do you have something similar for finite?
Not anything right now. No. Sorry. I mean, like in terms of things like
conjecturally even. Oh.
Yeah, I mean conjecturally, like I mean, it should be, like I mentioned, it's kind of in the same. It should be in the same territory as just mean field, like non-amenable things. In non-amenable graphs, you have this extra complication that you have like a phase where you have multiple infinite clusters, and maybe uniqueness phase. So things you have some different behavior. But in this general finite, like high degree finite transitive graph, not really. Of course, for the bounded degree sequences, then they should really relate just to the limit graph. So the features of the limit graph should be apparent in the, the finite size scaling of that should be apparent in the sequence of graphs. So if you take a sequence of tori converging reasonably to the Euclidean lattice, it will depend on the dimension and so on. But no, beyond that, no.
Okay, well, thanks.
Oscar, you had a question.
Hi, thank you very much. I was interested in the sort of the theorem you showed that connects the finite and infinite percolation. I'm just giving out the read over now. I was wondering if is there some sort of converse of that, in that if we find the percolation threshold for these finite graphs, that can give us them for the infinite graphs instead?
The threshold or the density, or which one was it?
Sorry, the threshold.
Yeah, so I mean, if the analog of this conjecture is true, then by knowing the threshold along the sequence, you would obtain the threshold in the limit graph, because it would converge to it. In general, you do also have like one of the directions is actually sort of trivial, like the lim sup or the lim inf of the sequence beats the limit graph one. So you have one direction that's kind of trivial. The other one's the one you want to prove. But yeah, certainly if this conjecture is true, you can derive the limit PC from the sequence PC.
Awesome. And my second question was, what are the conditions for the sequence of parameters to be a constant and not a function of n? Because I noticed in the Erdős-Rényi they were a function of n, and in some cases you state it as constants instead.
Right. Yes. So the question is really like whether so essentially if you're a bounded degree sequence of graphs, then your percolation threshold is always bounded away from 0.
Okay.
So you can pass to a subsequence where it converges to a constant, and then being supercritical is the same as exceeding that constant. And in general, if you converge locally, it should be a constant. Now, for high degree graphs, we can actually show that what typically happens, unless you're one of these macromolecular unusual things, then actually no, sorry, I shouldn't say that. Typically, what happens, unless something discontinuous and bad happens, is that your percolation threshold should be of the same order as 1 over your degree, as in the complete graph and the hypercube and things like that. So in that case, the threshold's going to 0 rather than bounded away from 0.
Awesome. Thank you very much.
Thanks.
Great. I can't see any other questions, so speak now if anybody does have one. In that case, I'm going to just stop the recording, and then I propose we give Philip a big round of applause for a beautiful talk.